By the way, Ron, in the transcript I'm doing of my last talk, I've turned your question before the talk into a whole little analysis of that paper about splitting photons.
Oh,
Uh,
awesome.
yeah, I put in some references, give some quotes from the paper. It's quite an interesting little issue there.
Well, that just boggles the mind that I assume there is no physical apparatus that can do that yet, but
None whatsoever. It's an entirely
yeah,
mathematical paper. The
wow.
illustration that you mentioned, in fact, was done by AI and is almost completely irrelevant to the
Yeah,
actual paper. This is one of the problems I have with AI because that figure it says it says something, but the actual figure is just a simple sinusoidal in the paper and a purely math analysis starting with an impossible physical arrangement. So it's a very theoretical in the sense that it cannot be implemented, and then they put some qualifiers to make it a little more real.
yeah.
So, but that's what makes it interesting is just to see both the paper and how the paper developed.
Yeah, I think the thing that triggered me is if that was something that is possibly real, it means photons are three-dimensional objects,
And but
or at least two-dimensional.
that is why I found it so interesting because what that did is provoked me to put together some things to talk about the three-dimensional shape of a photon. And so I've added a slide to the presentation specifically on that issue. And that's a little bit separate from the splitting part, but there is a three-dimensional issue is a very interesting part of that. So and relevant to a number of things. So great
Uh,
question. That was a good dialogue.
I'll be looking forward to your dissertation. It's like the more you learn about that stuff, it's like then all of a sudden, oh, well, and this, uh, I don't know. I think it's when I saw that graphic, it's like, oh, it's a photonic cigar cutter, you know.
uh, and despite the illustration, in fact, the illustration, if anything, I think minimizes that part. The illustration just shows a photon kind of bursting into a shower. The actual
Yeah.
paper really is more cutting the photon in half. I mean,
Wow.
they
Okay.
have sinusoidal and they chop it, and that is a realistic experiment. So that's the AI doesn't know that though. The AI just says, "What's a spectacular figure?" So it's the classic problem with AI is it gives really impressive figures that never have a good understanding of what the author was trying to convey. So in this case, it was a different group that created the figure from the people who did the actual paper. So a lot of interesting issues, but this idea of three-dimensionality of photons is a very interesting issue for a number of reasons. And it is meaningful to talk about splitting one in half. You could have it where it's gone, you can't split it. You split it if you catch it the right moment. Those are some real questions that you can do. So intriguing.
Like I said, I look forward to your presentation.
Terry, I'm still trying to get over electrons having a lifespan of 66,000 Yoda years.
I had not heard that. Is that an actual estimate someone's done?
Yeah, I just put the link in the chat.
Oh, I had not heard that. In my own for whatever it's worth estimate is I think the universe will not last that long. I at some point Penrose really did convince me that we are a cyclic universe in some sense, but not in the expand shrinks something form. It's something more complicated. But yeah, what was that? Yada years?
Yes.
Yada years. I love that preface yada. That just it's fun to say.
Being invited to talk on this subject, it's something I'm pretty passionate about. So I won't waste any time introducing me. I think most everybody here knows me. So I will just so welcome. I'm Ron Schreiner to Quantum Computing for Business. We'll be exploring opportunities that are available today. What we'll cover in this presentation is what is quantum computing, where is quantum computing useful, We're going to cover some actual use cases that I've worked on and have successfully demoed. And to wrap up, we'll be doing a brief review of the futures, some of the quantum computer types, or some of the things happening in hardware land. Now, this presentation was initially targeted at business leaders. I've added more technology to it, given the nature of this group. So as we go through, you'll see that there is more detail. Generally, we don't go too deep into explaining some of this stuff to like a board member or something like that. They generally have short attention spans. They just want to know how it's going to make money for them. So with that in mind, we'll jump right in with what is quantum computing. They harness phenomena discovered during the studies of quantum mechanics of very, very small particles, subatomic particles, for example. The phenomena that bears to quantum computing is the concept of superposition, entanglement, tunneling, quantum tunneling, which is very important with the quantum annealers we'll talk about. Quantum computing combines quantum hardware with computer science and mathematics to solve complex problems. Current solutions are based on hybrid quantum and classical platforms with access via the cloud, and that's pretty much true for all the quantum computers. Quantum computer by itself is not much good. You can't speak to it in any normal language. You need some sort of you need a whole infrastructure around it to make the whole thing happen. So we're going to talk a little bit about what are the difference between classical versus quantum computers, and we're going to go. Actually, this is a slide we will show them, show a business person, and then I've got extra slides that I'm going to drill down on. But basically, classical machines are based on bits. They can be 1 or a 0, and they maintain their state indefinitely. Quantum machines are based on qubits. They can be a 1 or a 0, or both 1 and 0 at the same time. That's known as superposition. And there's a lot of discussion about that. Someone might say that it's an infinite number of states between 0 and 1 simultaneously. A qubit will only maintain its state for a short period of time. This is the coherence problem. Classical computers use binary logic, and the circuits are based on digital gates and wires. Digital circuits run consistently. So as we'll see, if you have a digital circuit, as long as you leave the power on it, it will consistently process that logic, continuously and consistently process that logic. Quantum computers use quantum logic and sequential events based on quantum gates. And I have to say, quantum gates is really a poor choice of words. These gates are manipulated with radiation pulses. These are the sequences are referred to circuits, but when you really get into this, what you're looking at is something that's closer to sheet music. And it executes just like a song from left to right. Once it plays, it's done. If you want it to compute again, you got to reset up the circuit and re-execute it. So again, I'm sure someone who just chose the word gates because they didn't know, they couldn't find a better word, but it's very confusing. It's not gates in the same sense as digital gates. Digital circuits and programs are deterministic in classical world. In general, they can be relied on to always produce the same result for a given set of inputs. And of course, there's always the random stray cosmic particle that might upset your computer. It happens. I'm sure it's an incredibly rare event. But for the most part, you set up a digital circuit, it's always accurate for the vast majority of the time. Quantum circuits are probabilistic. Much of the current hardware technology is subject to environmental noise. In general, you don't always get the same result for each execution. Well, you never really get the same result result. That's why when you learn about running programs on like IBM gate-based machines, you don't run it once, you run it 500, 1,000 times, and you average the results to get your final probability. Classical machines run at room temperature and have in many different types of environments, like your cell phone to a microcontroller bolted to the side inside of an Abrams tank. Very harsh environments to very normal environments. Quantum computers require large amounts of specialized apparatus such as supercooling refrigerators. Most of the quantum hardware that needs that kind of refrigeration are chilling their qubits down to what they refer to as millikelvin. For the normal person on the street, that's essentially minus 460 degrees Fahrenheit. I don't know how anybody can wrap their brain around it. Coldest temperature I've ever physically experienced is minus 40. So that's well over 10 times colder than that. So now we'll drill down on those concepts a little bit. Again, classical computers are based on bits. So as an analogy, we use a coin. We can represent the classical as being the coin is heads up or the coin is heads down or state 0 or state 1. Never can it be anywhere in between. And in fact, most digital hardware engineering has to do with the fact that you got to make sure that you do not ever measure this bit while it's in transition. While it's in transition, it's called a metastable state. And that's why CPUs have clocks, or for the most part, they have clocks. They have extensive engineering to make sure that that never happens. I can only read it when the bit is in a known stable state. On the quantum side, a qubit can be represented as a spinning coin. As you can see in this animation, I don't know, I hope this is presenting well to everybody. This coin is spinning, so we don't know what state it's in. But the other thing I hope you can kind of see here is this coin is spinning on more than one axis. In fact, it has a vertical spin plus a slight precession to it. You can think of these multiple axis of rotation as being the phases, the internal phases of this qubit. And as such, depending on, you don't know what the final state of this is going to be until you measure it. Now, in our coin analogy, measuring it is slapping it with your hand and seeing which face is up. But the probability of which face will be presented is actually controlled by these different spins, or in actual qubits, they could be referred to as phases. Now, also imagine that this thing is very susceptible to external influence. If you're looking at this spinning coin, a physical coin, a little puff of air can make it go faster. It can change the axis of orientation. It can essentially change how the thing is spinning, and thus you are manipulating the state of the machine, of the qubit, or the state of the coin, and you're going to be adjusting the probabilities of what side will be shown at any given point in time. Now, what I probably might want to do someday is show two coins spinning together, because then you could imagine that if this coin is spinning and it's like giving off air currents, they might drift across to another coin that's spinning that's very close to it. And in that sense, these two coins are going to interact with each other, or they're going to become entangled. So again, this is just an analogy to try to explain to business leaders what the primary difference is between classical and quantum, and basically it's how the information is represented. Here again, we'll dive down into binary logic uses these circuits. And again, this circuit on the left will run continuously as long as you apply power to the circuit. It'll continuously compute the output based on the inputs. And then I think this is a, I remember right, this is a full adder circuit. On the right, we see what, again, what's referred to as a quantum circuit, but it's actually, I would more refer to it as a quantum tune. It's a sequence of quantum gates, which are events. They only happen once. You play this tune left to right. So the first thing you generally do is initialize your qubits to known states. You run this sequence of events, and then you do measurements to get your result. As I mentioned before, once you run this circuit or you play this tune, it's done. To run it again, you got to reload the quantum computer, reinitialize the qubit, reload the sequences, and play it again, Sam. And of course, you need to do this several times so that you get an average of what the result is. And this also lends to, digital circuits are very deterministic. We talked about that. You're always going to get the same answer. Quantum circuits or quantum sequences are going to return you a probabilistic answer or a probability distribution. So for a lot of people, especially when they start learning this anew, this is a kind of a hard concept to get your head wrapped around. It's like it's a 50%, it's an 80, 85, 90% accurate. It's like, okay, well, it depends on what what algorithm, what problem you're trying to solve to make more sense out of whether that's worthwhile or not. You talked about, classical computers work at room temperature, and here's just an array of all. I mean, classical computing is everywhere. From a laptop to a cell phone to the 25 Arduinos and Raspberry Pis I have on my electronics bench to you name it, they're everywhere. They run to the multiple components inside your modern vehicle that run the engine, run the entertainment system, and all that good stuff. They're everywhere, and they will operate in all sorts of environments, everything from pretty cold to military hot. So on the opposite side, on the right, quantum computers need a very specific environment to work in. Of course, everybody knows this is the big gold chandelier, and they think this is the quantum computer. And we always have to explain the quantum computer is a tiny little chip right at the bottom of this thing, and it's about, I don't know, maybe an inch square, maybe less. But this whole apparatus is designed to get that chip down to the temperature in the range of the millikelvins. And this is why we don't have them in broad distribution. They're in very specific facilities, and we can only access them via the cloud. But that might be changing. I'll get into that a little bit more as I go on here. Next, I want to would explain to them some of the different quantum computer types that are out there. And we need to do this for business people because there's a lot of hype. Everywhere you go in the media, you hear that quantum computers aren't ready for prime time. They're not. They can't do. They can't do any real work. Now that is about 95% true, but there are certain quantum computers that excel at solving certain types of algorithms, specifically complex optimization problems that can be formatted in some sort of binary quadratic. The quantum annealers in specific, and to some degree the neutral atom machines, can solve these things at a scale where it's either well beyond, like the annealers can go quite a ways beyond what classical can do. The current neutral atom machines are the ones that I've worked with. can they can go beyond what classical will do. They just don't go that much farther beyond yet. But the neutral atom machines are in their infancy. We'll get more into these. Um, so basically, and there's more technology than what we are showing here. Uh, I'm sure I haven't heard about every different type of qubit that's out there. An upcoming favorite is photonic computers, and I'll talk a little bit more about that as I get going here. Um, let's see. So we'll drill down a little bit on the various types. Superconducting computers, they're based on Josephson junctions. I actually met the gentleman who is credited for naming these transmons. It's a word I don't hear much anymore, but when I was out at the Pittsburgh Quantum Institute's thing a couple of years ago, and he's actually embarrassed that he named him Transmon. So maybe that's why the name isn't sticking so much. But they have the worst coherence times. They don't want to stick around for very long. Of course, all the manufacturers that are using transmons are making improvements every day, but it's still an uphill battle. Um, Involves microwave, for the most part on transmon, it involves microwave pulses to manipulate the state of the qubit and to do things like uh, um, do entanglement and do qubit to qubit stuff. Is somebody annotating on the screen? Please, let's not do that. Uh, Noise is a major factor. I mean, they're very susceptible to environmental noise. Um, they generally have a poor, what I refer to as a poor dimension of topology. Specifically with the IBM machine, each qubit is only directly connected to two or three of its neighbors. In my opinion, this is even more of a problem than the coherence time. If you have a very large algorithm that needs to use a lot of qubits, and the complexity means that there's a whole array of qubit to qubit interactions. The IBM compilers spent so much of their time minimizing the distance between qubits, and they can never really get it perfect. So what they wind up having to do is insert swap gates to virtually move the state of a qubit around because they can't physically move their qubits. So I'm going to talk more about this in the final stage, but what IBM has actually lately talked about. Um, and again, some of the newest stuff on the block is um, uh, the photonic quantum computers, and there's different flavors of these, and they basically uh, harness photons, the fundamental particles of light as qubits, and it's basically it's the interaction between smashing them together and pulling them apart. And I don't really. This is the least for me personally. This is the technology I know the least about. But there's at least one company who has avoided doing true qubits, and I'll talk about it in a little bit here. And they're become another version of an annealing quantum computer. Um, and you can see that in this diagram, it shows there's lots of lines where the elements can interact with each other. But again, this probably presents a poor dimension of topology. It's not like any qubit can speak with or can connect with any other qubit. But given the fact that these are photons and they're in transit, maybe someday they will have a way where they can just manipulate the photons to get next to their whatever neighbor they want. I don't know if they're working on that, but that could be some future work. Um, Photons maintain their quantum coherence quite a while and over long distances. This is why in quantum networking and like quantum key distribution, they always use photons and fiber because they're going to you're going to create a photonic qubit, set it to a state, and then they're going to fire it down a fiber, and then it's going to be processed on the other end. But you physically have to send the whole photon. You can't send a copy of it. So, but they're ideally suited for networking issues. This is one technology that doesn't require cryogenics or any kind of cooling. It just happens at room temperature. Some of the companies using these are Xanadu Orca Computing, Quantum Inc., and a new company that I'm just getting involved with, QCI, which I'll talk about a little bit more. And of course, Psi Quantum. For those of you that don't know, Psi Quantum is building a huge uh, um, quantum computing farm here in Illinois on the new Illinois Quantum and Microelectronics property, which used to be the old U.S. Steel Mill, and that's a big thing here in Illinois. They've actually allocated quite a large chunk of that property, and they're going to build a large farm of uh, of their uh, um, their quantum computers. Again, they're based on photonics, so um, they might have some networking capability, but they would still have issues with like distributed processing because again, you can't make a copy. There's the no cloning rule. But with a large enough array of quantum computers, uh, eventually you'll be able to access one of their machines, and there won't, gone are the days where you have to live in a queue. Like we first started with IBM, you have to wait several hours for your job to sit in a queue before it would get run. Psi Quantum has this promise that they got thousands of machines. Obviously, you're going to get access to one pretty quickly. If thousands, if not tens of thousands, I don't know. Photons eventually do get lost, so there, the people that deal with uh, fiber and fiber-based communication kind of understand a lot of what the problems will be. Neutral atom is one of my favorite type of machine. It involves suspending really heavy atoms in ultra-high vacuum by using this concept of optical tweezers, which is implemented by a pair of laser beams. You can kind of think of it like from your high school science class where they would suspend a ping pong ball at the end of a blower, like from a vacuum, and the ball would just kind of hover there, being trapped in the vortex of the thing. It's something similar to that, but it can also the optical tweezers can specifically position the atom anywhere in that vacuum space, and this gives them the ability to like in the case of this one that's shown, this is QARA's, a kilo processor. They have 256 neutral atoms in there, but they can physically make the adjust the positions. Now they do it in two-dimensional space, where they can adjust the positions so that it can map your problem. And one of the things they demonstrated early on was a problem of finding the next location for your favorite coffee shop. Well, they actually made the atoms look like a map of Boston, and where the existing coffee shops are. And then they run an algorithm that is to predict where the next best location for a coffee shop should be. That kind of sounds trivial until you realize that if the map's got over 50 or 60 current locations, you've outstripped the ability of classical machines to get a reasonably high quality answer. Whereas the neutral atoms have a way of leveraging. It's almost like when you position them in a random pattern, each neutral atom appears to know the distance between itself and every other atom in the array simultaneously. And it's kind of an analog mode of quantum computing, but it's very powerful. Now, in this particular vendor, QEra, at the time that I was working with them, they did not have true qubits. They operated their qubits in this analog mode, but you could get a lot of work done. It's similar to the annealers. You can they're good at very specific problems, but you can't do general purpose quantum algorithms. Although they claim that they did have a route to uh, making their neutral atoms perform all of the criteria required to be actual full-blown qubits as per the DiVincenzo criteria. There are a number of companies doing neutral atoms. Uh, there's atom computing called Quanta QEra. I actually had the privilege of going to Boston and meeting with them and essentially getting in the room where this device was. And they were so gracious. They even took me through their R&D lab to show me what the next generation of the physical hardware would be. Um, uh, and I'll talk a little bit more about these again when we get into the future things. So this neutral atoms have the best topology index because you can literally bring any two qubits together, by using the optical tweezers and manipulating them. So that's going to be a huge advantage once they get full gate-based operations capable. This particular machine has 256. This technology looks like the barrier to scale is not have to do with the qubits. It has to do with the support structure. There have been academic projects that have built neutral atom machines with up to 10,000 neutral atoms. The only issue is you wind up having to manipulate positions, and you have to manipulate these atoms in bulk because you can have 10,000. If you had 10,000 neutral atoms, there's just no room for 10,000 sets of optical tweezers. So they use techniques like optical lattice to move them in chunks, kind of the way a Rubik's cube works, where you're spinning things around in multiple dimensions. But that's all possible. Now, one thing QEra did, or QEra actually, their benefit, they're highly connected. QEra's plant is right across the street from MIT, and they work closely with them. But they've already come up with a way they can do. I think they have a prototype where they have two layers of 256 atoms, and they can slide them in bulk alongside each other. And in one operation, they can get all 256 qubits in both planes initialized. And in another operation, because they share the same grid, you can cause 256 entanglements with just one operation. So lot of efficiency can be had there. Just like everybody else, they're in search of logical qubits. That's another thing that they're working on. Another big player that's been around for a while are trapped ions. They also use heavy atoms. If memory serves, they're not quite as big as what neutral atoms do. And I should have mentioned on neutral atoms, they use these big heavy atoms because they're inherently stable. They're less likely to be interfered with by the environment. Trapped ions do the same thing. Instead of manipulating them with optical tweezers, they are trapped in magnetic wells and manipulated. There's a couple of companies that do this. IonQ, Quantum Factory, Alpine. Some of these companies, I'm not sure if they're still around. Quantinium was a company, it was a merger between Cambridge Quantum and Honeywell Industries. There's probably, Quantinuum and IonQ are probably the major players there. One thing that you'll hear about these guys is they don't seem to have been able to get past 30 qubits or 40 qubits. I don't know if there's a reason why they don't scale, but what they're working on is a way to. So, for example, in this photograph, uh, what happens here is you can think of it as like a dog bone racetrack inside there, and when the qubits are in this middle piece, that's when they can interact with each other. Uh, so they think they can have a way where that they can provide additional channels to additional copies of this. I'm not exactly sure where they're at with that, but that might be one way they can scale. Um, just like neutral atoms, trapped ions are generally stable, so they have better coherence. As far as the topology issue, it's not the worst, it's not the best, it's somewhere in the middle. Because although you can't speak directly to your next door neighbor, you can speak to maybe 25-30% of your other neighbors at any given point. Actually, that number might actually be higher, may even be above 50. So topology is actually pretty good for this technology. Um, we'll have to see whether they can overcome the scaling so they can get up into the hundreds of qubits more easily. Now we get to quantum annealers. These are special type of quantum computers. Their qubits aren't full-fledged qubits. In some cases, like in the case of D-Wave, they use transmons. They just don't operate them as full-blown qubits as per the DiVincenzo criteria. However, what they did concentrate on is they have a topology index of 20. So each one of their qubits can directly speak with 20 of its closest neighbors. That's way, way better than, again, that puts them about in the middle. And I'll talk a little bit more about them at the end. The other thing that's new is, again, QCI is is an optical based quantum computer, and they've also opted to just create quantum annealing type of machine. What is a quantum annealer? Basically, it leverages the concept of quantum tunneling um, to has the ability to find the lowest energy state of a system, whatever system that you load into the thing. You send it through its gyrations, and it finds you the lowest energy state. The quantum tunneling allows you to get there faster because, as you can see, it doesn't have to go over the classical paths. It can figure out that, hey, I'm in a false minimum, and I need to jump over this peak and or tunnel through it. So again, this allows it to find the lowest energy state of a system. That's actually a very useful thing, which allows it to again solve these binary quadratic problems, which is what you can reduce a whole lot of quantum optimization problems to. And that's why annealers are incredibly good at solving uh, quantum or solving optimization problems. Unfortunately, right now, that's about all they're good at. But for business, uh, from a business standpoint, you probably don't care that it's not a full-blown quantum machine. All you care about is whether or not it's getting you a better answer, it's saving you some money, or it's giving you some sort of business advantage. Um, let's see, we'll move on. So now again, we would talk a little bit to the business people about, where and when would you use it, and when is it a waste of time? Um, uh, first we'll talk about what are things that it doesn't do well, or you wouldn't waste your time doing it. Actually, a quantum computer struggles to do basic mathematics like add 2 + 2. Actually, that was one of the assignments I had to do for the IBM class, and it's basically you're building a one-time use thing, and it can only add 2 + 2. It can't. It's not a general purpose adder. This is why you won't see it powering spreadsheets. You won't, and another reason why you're not going to use one to balance your checkbook is because of that whole precision issue. It's generally not going to fit on your desktop, at least not yet. Again, I wrote this a while ago, and we'll talk more about. There is one that just might fit on your desktop. The other thing with quantum computers, you don't want to waste it on problems that are too small. You want to use it to attack problems that classical machines are just going to fail at. Where do they excel? Again, finding problems that are too complex for traditional classical computers, and in general, from what we've been doing, this always aligns with optimization problems, like optimizing financial portfolios, optimizing supply chain, logistics routing. The logistics routing is essentially the traveling salesman problem. It kills that. It solves those very easily. Some people claim they've used it for analyzing risk. I haven't actually dug into that too much, but again, any optimization problem, you can reduce to a binary quadratic or one of the similar flavors. Generally, these annealers will have a good chance of solving them. Optimizing resources, like where to locate high value assets like transmission towers or recharging stations for your drone fleet. Yeah, they are coming. Or scheduling a large workforce. Um, uh, this is a problem that shows up in all sorts of industries. But this is where these are the areas you want to uh, attack. You want quantum computers to attack. The following slides are these are demos that we've specifically done or I've done. Um, the main one, and we'll go through a couple of these. Use cases workforce scheduling, and again, this is for business people. We want to explain. So we try to explain to them, why do you want to optimize your schedule? Because this is optimizing a workforce schedule. It has, tangential benefits. So we try to get them to understand why you'd want to do it. Because you always want to avoid overstaffing. That just wastes money. If you minimize understaffing and your workforce is facing the population, minimizing an understaffing can lead to also customer dissatisfaction. It's going to learn to also cause employee dissatisfaction, and which will result in employee turnover. Employee turnover is more expensive than people know, especially if there's any sort of training involved. If you get constraint inputs from the employees, this leads to higher morale because the employees start to believe that they have a say-so in what they're doing. Constraints related to employment rules and laws can help to guarantee compliance and keep you out of trouble. Quantum solutions are faster with way fewer constraint violations. And so now this particular one, I'm going to actually show you the results of the demo. We ran, excuse me, we ran this for 80 employees, 14 days, multiple shifts. We had hard constraints, which is when an employee can not work. We had constraints, the max number there's a constraint, based on probably some labor law of the max consecutive shifts they can work. We have a hard constraint that you need 2 supervisors per shift. Soft constraints would be employee preferred shifts and slots. Employees tell you when they would like to work, but they're not guaranteed to get those slots. In a classical solution, this is run for like 4 hours per site, and the result was they had about 10% soft constraint violations and 1 hard constraint violation. Now, hard constraint violations, after you ran it for 4 hours, that 1 hard constraint violation has to be fixed by a person, because, or what are you going to do? Just run this thing for another day and hope it gets lucky? The quantum solution to this took 18 seconds per site and 1.5% in soft constraint violations and 0 hard constraint violations. And again, instead of 4 hours, it did it in 18 seconds. Now, this is really the benefit to the business. There's a large grocery chain company in Canada that is using this technology as we speak, and they claim that they've reduced their scheduling problem from a 3-week ordeal down to 8 hours. Their scheduling problem is way bigger than 80 employees, but those are very, very good results, in my opinion, or anybody would see that as a huge win. So on to the next one. Quantum computers are really good at solving complex, or basically graph problems found in computer science. In this particular demo, we were doing computer load balancing. So if you see the graphic in the upper left of the graphic, the red dots represent processes and the gray edges indicate communication channels between the processes. The task is we need to map these processes onto, we have 4 servers we want to map them onto. So the goal here is to come up with a division of this graph such that we minimize the number of server-to-server communications. If you look at this problem, it actually had over 100 process nodes and many more edges. If you add that all up, let's say that would give you about 300 constraints. That's a 2 to the 300 problem, 2 to the 300 size problem for classical machines. Once again, the quantum machine was able to solve this in about 15 to 18 seconds. And the result is shown in the lower right of the graphic, where it got it down to the point where there was only 2 server-to-server communications required. And the one person, there was one person that said, "Well, how do we know you didn't just preload or predefine the data set?" It's like, well, this was generated totally by random, given a set of the initial graph in the upper left was totally generated by random, given a set of build probabilities. And we ran this for a couple different times and got basically very, very similar results. This can also be used we use this particular demo is for load balancing computer processes, but you can also use it to locate clusters and populations, splitting social networks into groups based on relationships. I saw one paper on they were using this exact same algorithm to locate security cameras in a high security environment, and also use the same algorithm to locate antennas out in the field. so that they were optimally placed. Could also use this to locate customer service centers and make sure that they're positioned such that they give you the best coverage over your customer population. And of course, just like with the neutral atom guys, you could use it to locate your next coffee shop. So, in this one, this was actually this one wasn't actually a demo, but this just indicates some of the other types of graph problems that actually we actually ran these on the neutral atom machine because even in the analog mode uh, solves these pretty nicely. So minimum independent set, max cut, minimum vertex cover. These are all things that are defined in um, uh, in computer uh, um, defined as computer problems that are well known to be hard to solve in some cases. Um, and I think we're getting towards the end. This is another use case that we demoed. Uh, obviously you do this, you want to find the shortest paths. You can use it to optimize your supply chain. This particular problem actually solved multiple routes simultaneously. Obviously, if you have a large enough fleet and you can reduce your gasoline consumption by 10% a day and you're spending $1 million a day, this is a big win. Companies like Amazon or FedEx or any sort of delivery, anybody putting wheels on the road could easily take advantages of this. I'm assuming these huge companies are probably looking into it. What we're trying to do is bring this to smaller companies who maybe they don't have the huge budget for an in-house quantum team. This is also used for optimizing transportation scheduling. There was a project in the Netherlands where they used it to reduce rider wait times. And there was one other project where they used it to guarantee coverage of what they call the um, uh, it's a honor system for paying for your tickets, and the honor system allows them to eliminate a lot of things like kiosks and stuff like that. So basically, you buy your ticket, you get on the train, you're subject to a random search to see if you're valid. And what they did is they came up with an optimized a way of setting up those check sites. But in the long run, they're able to do is eliminate a lot of kiosk stations with minimal impact to revenue. So very, very cool use of quantum computers. Uh, in the particular demo that we ran, there's 5 vehicles, 100 pickup locations. Again, 100 pickup locations, you're over the limit as to what classical can really hope to solve, um, other than just doing heuristic guesses at what's going on. You want to minimize your vehicle route length and travel time. Our goal was to minimize vehicle route length and travel time, minimize vehicle to vehicle workload differences, and make sure all the vehicles were at similar load factors. Classical machine was allowed 2 hours, and basically what it does, at this size of problem, it runs for 2 hours and it saves the best result, and that's what you get. Run this on a quantum computer, allocated 15 seconds, and on average, we got a 12% better solution than classical. Again, this is just over the limit. You would have to spend a little bit more time with a quantum computer if you had a much larger problem here. But again, this is already out beyond the grasp with classical, just based on the complexity. The other thing I want to point out here is this is actually solving multiple optimization problems simultaneously, because not only is it optimizing a vehicle's route, it's optimizing which route each one of these pickup sites should belong to. You can see here in the center of this where it's real dense. This could become a problem. And there might be other constraints involved with this, but it solves this with one algorithm. It figures out which, again, it figures out which route the site should be on, and then it optimizes that particular route. So huge benefit there. Okay. This was another demo we ran. This was feature selection. Unfortunately, we don't have a really great graphic for that, but what this is, if you have a large machine learning project and you find out that your input data, you get thousands of columns of data. Generally, the first step is what they call feature engineering, where you want to get rid of the columns that are irrelevant, etc. There is a quantum algorithm that will find you the best M of n columns to use for your machine learning project, such that you basically get the same results. The one particular demo that we ran, it started out with 400 features and the quantum computer was able to select, of the 400, it was able to select 60 features that would either give you the same or if not better performance in your machine learning stack. So that would be like a reduction of like 80%. Of course, anytime you reduce the number of columns um, in your input, it's basically a one-to-one reduction in training time and a one-to-one reduction in inference time. It is a very, very hard problem to sell to people though, because you generally do it at the front end of your machine learning thing, and then you go away and you go on to your next project. But if you can reduce your training time, especially on a large project, by 80%, that's definitely, you know, depending on what type of project is and how often you would rerun that training from scratch, could in the long run save you a lot of money. But this is another computer science problem called M of n. Just like in computer science, we have the graph problems that quantum annealers and the neutral atom machines can solve. This is also known as a knapsack problem, and there's was different ways to use a quantum computer to solve the knapsack problem. Well, quantum annealers, I should say. This last one is basically my favorite because it included an interactive 3D visualizer. Uh, you need efficient shipping container packing. You need to be able to reduce the number of containers needed for a mixed ship, and eliminating a single container can save you up to 35 grand. This was actually a real number back towards the end of COVID. I think this number has come down a bit, but still, if you can do the shipment with one container instead of two, you just save some money. And even if it's $10,000, you saved quite a bit of money. Warehouse inventory planning to optimize storage and retrieval based on multiple constraints is also something that could be done with this algorithm. In our particular demonstration of this, I actually had one experiment that had 38 packages of random size. We were using a medium shipping container. We ran the classical algorithms for 50 minutes. We got 0 solutions. The reason we got 0 solutions is because we have a serious hard constraint violation. And that violation is if they don't all fit in the container, it's a failure. Okay, so in the case of classical, after 50 minutes for this one experiment, came up with 0 solutions. The same experiment run on the quantum machine did an efficient pack within 15 seconds. And so in the real world, this would allow you to eliminate the cost of a single container. The other thing that you would notice about the pack is it was still efficient. You could still fit more packages in there. So In the shipping business, wasted, unused space is wasted money. A lot of shipping companies, as I understand it, accept a 60 to 70% full index. It's just the way, that's how you do business. So uh, this and again, because this was very three-dimensional, it was interactive 3D display. It was very powerful. Well, I mean, we normally talk about post-quantum encryption. I'm not going to do that today. So some of our conclusions would be quantum annealing hardware technologies are business ready today. Photonic and neutral atom based quantum computers are now becoming business ready. And again, there is at least one photonic computer that we've just started working with, which operates in an annealer mode and has the same potential to solve optimization problems as the king of annealers right now, and that would be D-Wave. And by the way, all those demos that I just showed you that we did, those were run on a D-Wave machine. Hard optimization problems are candidate for quantum computing solutions. But they, it's not, you got to make sure that the optimization problem you're looking at is mappable to a quantum annealer. Implementing quantum computing in business can be done using specific strategic planning. So now I wanted to talk a little bit about the future, some of the hardware. In the superconducting or transmon array, when I was in Washington, D.C., saw a presentation by IBM. They are finally getting around to the fact that their topology of 2.5 is topology index of 2.5 is really one of their major problems. They laid out at that conference a very aggressive roadmap that takes us to 2029. And one of the things we specifically talked about was a new interconnect topology mechanism, which they just labeled something called the grid. I couldn't get a whole lot of information over what the specs on that would be, but anything they do to improve that is going to be good for them. In the neutral atom area, again, what we're looking for is to ramp up the size of the neutral atoms. There are people who have, like I said, gone all the way up to tens of thousands. Not really. And there's also the issue of getting the neutral atoms to operate in a gate-based mode. Last I checked with QEra, that was something they were working on. I have to get back with them and see if they've succeeded with that. In the trapped ion space, I mentioned a little bit about, their one of their issues is scaling up to qubit size. They have talked about ways to do that, but I don't know where they are at with that. Quantum annealers, in the area of D-Wave, their next generation of annealers will have even a higher topology index. They've got plans to build in a topology number of 40 connections per qubit. So each qubit will be able to talk to 40 of its neighbors. That'll just make things better. Photonic quantum computers, again, we just started looking at QCI, which is a company that is building and shipping optical-based quantum computers that operate in an annealing mode. So I'll have more to report on that in the next couple of months, but it's everything that we've seen so far looks extremely promising. So I hope, other photonic companies may not be taking that direction, but from a business standpoint, they need to be looking at this stuff that's going to help business today. In the middle here, I labeled something called EHE. This is electron on helium. I don't have a good graphic for it at the moment because the machine doesn't exactly exist, but We some of you in the group may have been at our presentation last Tuesday by Nick Farina, the CEO of AeroQ company, who's building this electron on helium technology, and they've finally demonstrated their first qubit. The potential of this technology looks incredibly uh, um, doable in terms of they started out by addressing the topology problem because they started out by addressing the scaling problem. They didn't want to start building a qubit without knowing how they were going to scale this up. And I believe there'll be a recording of that if people want to go over to Quantum Computing Chicago, Illinois, and beyond on meetup.com. You might be able to find the link to the recording when it gets posted. But it's fascinating technology. It's actually a lake of helium that's super chilled, and and electrons have this tendency to stick to the helium somehow, and it has something to do with seeing their reflection through the helium barrier. It's just mind bending. Um, but they're able to manipulate electrons in parallel, so that addresses or in bulk, I should say, it's a huge advantage in the topology area. So that's a technology, and everybody should keep their eye on to see where they go. And AeroQ is based right here in Chicago. They're building these qubits right here in the city. So um, I believe that's all I have. So I want to thank everybody and can open it up to Q&A. Thank you. Anybody have any questions?
Yes, I see somebody raise his hand. Corrado, can you unmute and ask your question?
Yeah, hey, this is Kwejo. So first off, excellent presentation. Thank you so much.
Thank
I
you.
was curious, and my apologies, I joined late, so I may have missed a part of this. I was curious uh, of two things. Number one, how you first got into bridging the gap between quantum and business, but number two, also what uh, as someone on the research of photonics and science side, what the best way to learn initial steps for solving some of these problems and uh, uh, learning how to bridge the interface a little bit better would be.
Well, how I got involved with it, when we started our company, we got a nice contract with a big pharmacy company called CVS, and we became the quantum division of their innovation center. And our job was to go out, find the technology, learn it, and demonstrate it. Fortunate for us, they also decided to buy a big fat license from D-Wave. So we had essentially unlimited access to D-Wave. And it gave me the ability to go and basically exploit pretty much every demo that they had out there. And my challenge was to figure out how to map those demos onto something that would be understandable internally by by CVS teams and such. Um, so I did take training with the D-Wave, which takes you through the mathematics of binary quadratics and shows gets you well situated to understand how that gets mapped onto their annealing processors. Um, and I don't really see any way around that at the moment. Their framework, their software framework has gotten a lot better. So at the very least, you would, to get involved with them, you need to go and learn their software, because everything is a hybrid. So their software stack, it's nothing like the traditional Qiskit or Qiskit wannabes or whatever, because annealers don't work as gates. Uh, but they've made great strides not only in their hardware but in their framework, so that a lot of the low level stuff that you had used to have to worry about to do that mapping is being handled by library routines. But you basically build your constraint models, set your objective functions. The objective function can be thought of as a cost function, just like in machine learning. And then once you get that stuff done, you submit it off to a particular solver, which we'll take that information, map it onto the machine, execute it, and then bring you back the results to you. We also got started with doing this for the U.S. government before the U.S. government got stupid. But that's how we got into it. And that's how me personally, it was like I was head first into it. I wanted to basically learn everything about it at the time. But what I learned by doing this is this stuff works, and when you compare it against classical solutions, not all of their demos had classical components, but for example, that 3D bin packing demo had a classical option, which ran it against the 5 best known algorithms for solving that type of problem. And the more I ran it and the more I was able to play with it, I realized this will work for business today. Again, the caveat is it's a quantum computer that solves a certain narrow class of problems, but it really does a great job at it. This narrow class of problems, which we refer to as optimization problems, they appear everywhere in business. So we started realizing that we need to get out and ahead of the hype and say, yeah, because the media is out there telling all these people that it's not ready. It's like, for the most part, that's true, but in this particular scenario where you're trying to solve optimization problems, there is a quantum solution, and you can use it today. So, I'm sorry, what was the second part?
No, I think you answered quite a bit of that. I think the tail end of it may be, is there a way to get involved or to learn a little bit more and
Yeah.
bridge that gap without the 25K per quarter licensing fee?
Yeah. Well, in the case of that D-Wave, all their documentation is online. You can go read it.
For sure.
We've just started working with QCI, which is another annealer that we're very, very interested in, and so far we've gotten good results. We just negotiated some time on their machine, so I'll have more to talk about there. But again, you go to their site and they have all sorts of documentation. You have to be the type of individual who can self-lead your education. Just go through the documentation as fast as you can, and even if it doesn't make a lot of sense at the beginning, eventually, by the time you get to the end of it, a lot of times you realize, what you didn't know at the beginning starts falling into place and stuff. But you can also pay a D-Wave, for example, to take a specific class.
Oh, okay.
I mean, it is, I don't know what they're charging now, but it's not a trivial amount. But that's another alternative. And then you get to work with instructors for about a week or so. But I was waiting for. I took their class. I paid the money. But now they have a whole new breed of solvers, and I'm like waiting for them to update their class. and I would probably take that again because what they call their newer nonlinear solvers, you program them completely differently. It's not the same at all, but it's easier. It's like you don't have to worry so much about the low level details. You just describe the problem in terms of nonlinear nuggets, so to speak, and it just figures it out. So I mean
Amazing.
that's the best thing you can do right now.
Yeah.
And I'll have
Well,
more to talk
thank you.
about QCI when I learn more about what they have available.
Yeah, and that actually, funny enough, is my expertise area. So if you have bonus questions on the photonic quantum side, definitely let me know.
Oh, beautiful. Thank you.
Of course. All right, and thank you again.
Appreciate it.
I got a question from YouTube. It asks me, do you have any links for the EHE?
The company is AeroQ, EEROQ.com. There's not a whole lot of information up there. Um, again, I'm not, when the recording for our group from last Tuesday gets posted, I think you learn a lot more from that. But it's fascinating technology. It's just crazy. Anyway,
Ron, I
We-
noticed.
And Terry has a question, yeah.
No, I just meant I noticed that Wikipedia does have what looks like a nice illustration, but if you've seen it in the chat, uh, you might be able to say whether that's a reasonable explanation diagram for it. But Wikipedia does have a nice little article on it.
yeah, I mean the concept of electron and helium has been around a long time. This is the first company that figured out how to make it happen. Um, so I'll have to look in the chat for the link. Did you post it or?
Yeah, I posted the image real quick, and I think it gives a little visual idea of what it's talking about. But again, it's just from Wikipedia. It's
Yeah,
not.
this is probably from a very early research paper. Um, so this is showing that there's a helium superfluid that the electron just it's almost like levitation in a superconducting material. The electron just seems to it seems to be able to lock into some sort of pathway. And Nick talked about how it could see its shadow on the inside of the fluid. I didn't really get into the details of that, but it has something to do with lock. It at the very least it locks the distance from the electron to the surface of the helium fluid, so that it's trapped that way. And then they use channels to move the electron in 2 dimensions. But I'm guessing that this graphic that you posted is from one of the early papers. I didn't see this in any of their documentation, but it looks like it's pertinent, though. Yeah,
Could you spell the name of the company again?
it's EEROQ.com, and I probably need to double check that. I'm going to do this. Not my thing.
Yeah, that worked.
Yeah.
EERO capital Q. Yeah, I got it.
Yeah, yeah.
I'll put it into the chat.
Oh, excellent. Yeah, I mean, they've got some information there, and but it's mostly cartoons. But if you I'll let you guys know definitely when that recording becomes available, because he's actually got photos from electron microscopes incorporated in it.
That lock-in on the surface is fascinating. I've got to look up the physics of that. That's intriguing.
Yeah.
It sounds a little bit like electron hole pair type of. I don't know. I got to
The
look that
way
up. That is intriguing.
yeah, I had the same reaction, and I know little or nothing about it. It's like, it's just a magic phenomenon going on there. So
I've never
yeah,
heard of
it's
that.
cool technology. So could be just a whole nother area of quantum mechanics. I don't know.
Hey, Ron, it's Bill Slater. I had my hand up. I just wanted to mention something that's both amusing and tragic at the same time. Since you and I both I live in Chicago and you live in a northern suburb, there's all this drama going on about what's going to happen to the Bears. Are they going to move to northern Indiana and Hammond, or where are they going to end up? Because this is deeply emotional to people who love the Chicago Bears. Well, it was just introduced last week that one of the possible future locations of the Chicago Bears is going to be the same location of the IQMP, the Illinois Quantum Microelectric Park.
Not
So
likely.
yeah, so I know. Well, they're desperate. Neither Governor Pritzker nor Mayor Brandon Johnson wants that reputation of having lost the Chicago Bears. So they're trying to pull every rabbit out of every hat that they can. But I just thought it was amusing because we're all a bunch of quantum geeks, and now they want to put the Bear Stadium where a $9 billion quantum park is going to be, and say, well, it's okay, we got enough room down here, so bring down the Bears. It's going to be great.
I'd be very surprised. I know that Psi Quantum has already broken ground. But I don't know I don't know if that park is a better location than Indiana. But interesting enough, there's a guy in Chicago who's has written a series of articles where he's conflated the Bears issue with Pritzker's quantum campaign, because
Right.
Pritzker is a huge advocate of quantum. He comes to all the events. I was standing within, I don't know, 20 feet of him at the CQS last November. So I don't know. I think it's just more entertainment that they're conflating the two. But I don't know if that's a great location for them. I mean, it just makes no sense to me.
I
I
would
mean, how
agree
is it
with
better
Ron
than
on
where
that.
where they're at? I don't know.
I would agree with Ron on that. The location of the tech park is not really accessible either by car or public transportation, whereas the site in Fox Lake and Hammond, it's much closer to downtown, and it's available by both train and bus and car by the Skyway. So I really doubt that they'll be able to make that tech park work.
Maybe at the very least, some company convinces the Bear to declare them the official quantum company of the Bears, because that's how that stuff works.
I have a quick question. I am new to quantum computing and wanted to learn with the self-paced training or with access some quantum computing online. And what would be your recommendation to get started? on that path?
Um, so if you're interested in learning about gate-based machines, which will potentially be the future. I mean, they're going to get better. I'll tell you what, my path was to go out and acquire every book I could get my hands on that talked about quantum qubits and gate-based machines. And actually, we have an author here in our midst. Um, Professor Barry Bird is an author of a great book, and of course, I'm biased about that book, but it's an excellent start. And if not, um, it gets you through the basics of gate-based machines, the language of qubits, the basic mathematics that are involved. Without Barry's book doesn't go deep into the mathematics, but you don't really need to for most of the things you want to do. After doing that, I found out there was a number of summer camps or summer schools. I wound up getting personally, I wound up getting accepted on a scholarship for something called the Womanium Project. Went through their summer school, exited with one of the highest sets of numbers. That led to me becoming a fellow on one of their projects, and I wound up designing a quantum sensor for the U.S. Naval Nuclear Laboratory. But the important thing is just accumulate whatever you can get. Look for the summer schools. I understand that IBM is starting their summer school back up. It's supposed to happen soon. Definitely sign up for that. I believe it's still free. Um, uh, it would be more of an entry level thing, but I would tell you the summer schools are not easy. I mean, you gotta put time into them. There's all sorts of other places you can go to get free information, different entities. Bill Slater just published something about is that a free bill for the CERN that you put in here? Where is that? It's in the chat.
Yeah, Ron, it's free.
Yeah. So it's a course you can sign up for free. It's a course I developed at CERN now, out in Switzerland or France, Switzerland, whatever you want to call it. Look at that. Somebody posted the Kiskit Summer School 2026. Kareem, do you know what the date is on that? But that's where I would go. If
9th of July. So
Oh,
maybe
awesome.
in 10 days.
Yeah. I mean, you can also look at academic solutions or offerings. But when I was doing it, there were none if there was anything, it was only available to postdocs or pre-PhDs. I know that has changed. I know the school that Barry is a professor for, he teaches a class there. So you could look at that, but there's tons of free information out there. All I can tell you is, accumulate as much as you can, absorb as much as you can. Because if you just rely on one book, you're getting one point of view. There's many times when I'd be reading the second or third book, and they would present something in a slightly different way that would improve my understanding of a concept, such that I could go back to the previous books and go, okay, that's why that makes sense, or something like that. But definitely get involved with the summer schools. The major players like Q World. Here in Chicago, we have QBraid, which is a quantum programming platform. There's another quantum programming platform called Classique. check out both of those places, and every once in a while they have hackathons, they have competitions. They all have communities that you can get involved with. So you got lots of avenues there.
Thank you. I appreciate it.
Yeah, no worries. Any more questions?
So Ron, there were at one point some, optimization problem was done in financial market. Is there any more progress on this? You didn't mention anything today.
Yeah, we're aware of people doing that. It's not an area I wanted to get into because of the regulations and the red tape.
I see.
But the main play in financial, the main play, but there's more than one. The main play is, let's say you're a portfolio manager. A client comes to you, tells you what their goals are, they tell you how much money they have. They might tell you that, I don't want 1,000 stocks, I want 50, I want 40. So that portfolio manager's job is, of the tens of thousands of instruments that are available, what are the best 40 for that particular client? It's a it's a combination of the M of N problem and the knapsack problem. At those size numbers, again, classical machines have no chance. But you format that problem as a binary quadratic, map it onto an annealer, then the annealer shakes it down to the minimum energy level, and then you translate that back into a solution. And the other issue with that is the proof of viability is extremely intangible because they're stocks. And anytime you deal with a broker or a stock, what is the first thing they tell you? Past performance does not guarantee future gains. So it wasn't an area I wanted to get into for a number of reasons, but mostly very hard to prove without waiting a long time that your solution was actually better. So the other major area in finance is, and this was a thing that was in its infancy just a few years ago, but using quantum computer to optimally select the pathways in a causal graph that would lead to fraud. So they would use quantum enhanced fraud detection. I know some people worked on that. I don't know that anybody's put that into production yet. So but I mean, it gets listed. It gets listed as a place because it's an optimization problem. It gets listed, but not an area I want to go to.
Thank you.
Hey, Terry.
Yeah, a quick question. More than once I've encountered people using quantum simulators who, at least in my mind, were getting kind of fuzzy about the difference between a quantum simulator and an actual quantum computer. So do you have any comments or questions or comments about the use of quantum simulators versus these actual quantum computers for business?
So quantum simulators for gate-based machines are just basically these monster number crunching machines that maintain the state matrix for the problem. To my knowledge, but this is an issue because I saw a news blurb go by, I don't know, a couple months ago now, that huge data center in Germany, and I can't remember the name of it. They brought online an exabyte machine. They're talking about not an exabyte of hard drive, an exabyte of memory, just raw memory. I don't know how to wrap my head around that, but they're claiming that they have built a simulator for gate-based machines that I think it's somewhere between 48 and 52 qubits, but those are qubits that are implemented at full double precision on both the integer components and the imaginary components. But so that's a 2 to the I don't know, it's like a 2 to the 60 problem. So 2 to the 60 bytes of memory you need. So it sounds like an exabyte. That's the biggest simulator. Now there's people who build simulators that are taking shortcuts. I've heard of people talking about using the tensor libraries to take shortcuts, but they generally get you 1 or 2 qubit ahead of just raw computation. So if the simulators are great for fleshing out an algorithm. They run faster because they're classical machines. You don't necessarily. Most of the simulators have a mode where you just calculate the result. You don't run like a true quantum machine. You run a 500, you run 1,000 shots, and then you consolidate the data into an answer. Where the simulator, because it's doing precise calculations, you just calculate the answer. So, but the downside is you're just limited. You know, Eh, I think the average person, if they're lucky, they have access to a simulator that's doing 30 to 32 qubits. That's enough to do some testing, get some concepts laid out. But again, not big enough for a business size problem. Hope that answers your question. You're on mute.
Yes, no, that's I always find that area interesting because I'm very much a follower of Feynman's perspective that uh, you cannot efficiently emulate a quantum entangled system. It's not possible. So it's always interesting when I see these massive, massive computers. It's not that you can't do it. It's just that you cannot. It doesn't matter how big the computer is compared to what happens with these entangled systems. It's just yeah, that's where the whole quantum more fundamental advantage comes in with those. So just an interesting area on how big some of these simulators have gotten.
Yeah, I mean, absolutely. A real quantum computer might be reacting to some phenomena we don't even know about yet. And the simulators are just doing the pure math.
Yeah.
So, yeah.
Ron, did you have any general? Oh, someone else. I'm sorry. Somebody else's.
Well,
Yeah, I had a
Quado?
quite Joe, yeah. But I
Quadro,
had a
okay.
Joe like Joseph.
Okay.
Yeah. But I had a 2-second question on your last comment. How many qubits is typically big enough for a business size problem?
Well, that's hard to answer because people haven't even really addressed it. Like if you come up with an algorithm to do DNA matching or something, there's no point in using a quantum computer to test, even 50 uh, genomes or 50 what are they called? Because you can do that with a classical machine, where the problem has to be able to do thousands and thousands, if not millions of comparisons. Um, a lot of the algorithms that are out there that so gate-based machines can do optimization problems, but generally you generate a mapping of one constraint to qubit or less, because there are very few problems where one aspect of the problem has just one constraint. So solving a optimization problem that only has 50 constraints, again, classical machines can handle that. It's when you get into like some of these things we're doing, like with routing or employee things, we're actually dealing with hundreds and hundreds of constraints. That's a business size problem. So yeah, again, gate-based machines have the potential to do the same thing. It just they're not big enough, they're not wide enough, and they're not deep enough. That's why you hear people talk about how close are we to implementing Shor's algorithm. It isn't just the number of qubits; it's there's a coherence problem because part of the Shor's algorithm involves an inverse Fourier or a quantum inverse Fourier, and the depth of the gates to do that at a small scale pretty much convince you that once you get to large numbers, that not only are you going to need 10,000 qubits wide or whatever, you're going to need a machine that can run for 10,000 states or 10,000 cycles, and that this doesn't even remotely exist yet. So, I mean, people know where these algorithms can go, but I don't know if I could pick one area. Again, they can do the optimization specifically. They do the QUBO and the QAOA algorithms, but they're just you can't do them at a scale that is beyond the classical capability.
Awesome. Thank you.
Terry, are you hand up again?
Yes, yeah. First of all, I was really impressed with some of the successes you showed. I'm often a bit of a skeptic about how far they got, and you had some very nice examples where I love seeing that of actual businesses saying, "Hey, this improved it by 80%." That's impressive. And following up on that, do you have any, from what you've seen of the successes, for a business person who is not familiar with quantum mechanics, they're not a physicist, do you have any kind of broad advice for helping them to assess what they do on whether quantum computing is worth looking into that? Do you have any general guidelines from the successes you've seen on what they should be looking at strictly from a business viewpoint?
Well, that is a fascinating. I mean, this is a question that we deal with all the time. I don't want to be in the business of educating them on quantum mechanics or anything remotely close to that. I just, we need to just show the average business person that they're going to get an advantage out of it. And when I say advantage in that context, I'm not talking about a quantum advantage in the academic context. I'm just talking about they can get something done in a way that either save them money or give them an industry advantage, a competitive advantage that they can put their hands on or they can wrap their brains around. So this deck that I used, it's a ramped up version because this is a more technical group, but if we do this just for just straight business people, we do kind of, lack of a better word, we dumb it down. So we just basically give the briefest explanation that quantum computers are different. They work completely different. I'm not going to get into the details, but here's the use cases and here's the results. I talked about the grocery company in Canada. They've been doing this for a couple of years now. They've been in production a while. Another company in Turkey, it's actually one of the Ford motor assembly plants in Turkey, started using, I think they might be going to production now, but they did an expose into using a quantum computer to optimize how they got body parts through their paint shop. And again, people don't realize how tough can that be, or they'll have the attitude, how tough can that be? Well, the issue is changing the color on a paint booth is a big deal. It's very expensive. So you want to minimize those changeovers. And so they developed a quantum algorithm to optimize the workflow through their paint shop to minimize paint booth color changes. And they save a lot of money. And again, because of the number of constraints that are involved, classical doesn't really have a play except other than heuristic guesses. So, and
Would
then, pardon?
would minimization of costly changes be one of the criteria where a business says, yeah, I'm getting a lot of expensive changes, I want to minimize those? Is that
Yeah.
a good potential area?
Absolutely. And in fact, that's the core mechanism of the annealers is they find the minima.
Yeah.
So even if you're in you have a business problem where you're trying to maximize something, you just need to invert the algorithm so it's looking for a minima. And
I could see that connecting with business
Yeah.
managers because they see it.
Yeah.
They see it and say like, wow, this is really costing me. How can I get that better? And if they can suddenly realize, and I don't think many of them do at this point,
Yeah.
say that, if I went to a quantum computer, I bet it could help me with that. That might be an interesting thing for more business people to realize.
Well, and so the other side of that coin is there are companies out there who have drunk the Kool-Aid. Obviously, this huge chain in Canada, they were on board with quantum. Nobody had to explain it to them.
Yeah.
Even though they didn't completely understand it. There's like all they knew is they were spending 3 to 4 weeks a month to do a 2-week schedule, or to do it. And they got it down to 8 hours, and they just are like, we got to do something. In their case, we got to do something because this is not working. And so they took a leap of faith. They now have an in-house quantum team. So there are companies who the key is for us, or the great thing for us is we can find someone who's open to be an early adopter who wants to be a pioneer in their field. And I was actually I've been talking with one entity who's in the media business, a business I would have had no expectation there'd be a quantum play, but it turns out that if you're a large advertising company, you got a large client and they got a huge budget, and someone's got to figure out how to deploy that budget onto the various advertising instruments. It's kind of like the stock portfolio management. It's essentially actually the same problem. We found a guy who has already drunk the Kool-Aid. He's already decided that we don't have to sell him quantum. Um, uh, so that's when you get lucky. But just a general company, um, we've learned that you got to focus on, show them the ROI, show them the advantage, and it's got to be tangible. At least we want something that's tangible. So there's no dispute whatsoever that the solution is better.
Large scale logistics is such a horrendously complex and difficult field. And a lot of people know it. I mean, if anybody who's dealt with logistics, of course, a military in general are, as they say, wars are won by logistics, not by the front.
Yeah.
It just seems like logistics should be more aware of the potential of some of these examples.
Yeah, you got to cross their paths because they don't generally, circulate in our domains.
Logistics they don't think in those terms, and yet there's a
Exactly.
crossover there.
Yeah.
But they do think in terms of saying, man, this is a hard problem. And how to shuffle these things around, how to get them there. A couple of spectacular examples of someone doing logistics and seeing a good improvement. It just sounds intriguing. There's a cultural barrier to cross there, but they know how hard the problem is. Anybody who's been deep in that, they know it's hard. And if some technology could help them in a way that classical computers can't, wow.
Yeah. Well, yeah, I recently did a somewhat of a dive into workforce scheduling for reasons, and it's scary what the current state of the art in classical is. Everything from, we just give you a spreadsheet, you fill it out, and you worry about the constraints, to they have an adversarial system where it's kind of like the tulip. What do they call that? The tulip. Um, uh, oh, auction. The tulip auctions. They have a certain type of auction. So what the employer does is they put out the schedule, and they actually ramp up the price on time slots that are hard to fill, and then they wait for employees to come in and either bid on them or accept them. And the downside is what happens when you don't fill them all? Then you got to find people that you have to pay overtime or double time to. It's like, how is that a solution? They just completely sidestep the problem. But that was what I found out there that's currently being used, especially for large workforces. Just documenting your failures and put it in a system that will almost always fail you. And again, in the case of workforce scheduling, all hard constraints have to be resolved by a human, and that's where it gets real costly.
Surreptitiously in the background, some of the biggest company successes are also companies that are using better methods where they're not just using some sloppy, simple method. A good logistics system, going back to that example, is a wonderful thing to behold, and it involves all sorts of things of predicting the future when you can't always predict it. But there's a huge opportunity there that's demonstrated by companies and governments that have succeeded in doing good systems. But those good systems are classical right now, so it's just intriguing.
Yeah. Yeah, it's not getting to the right people is not a solved science, and something we're learning every day. So, Joe, Joe again.
Hey, one more question. I can't guarantee this will be the last one, but I'll try to make it quick.
Okay.
So you brought up something very, very valuable in a like 3-word context. So mapping the problem, right?
Yes.
That I think is probably an extremely overrated step. Because my thought process is, let's say I meet someone at an airline, for instance, and they have a huge logistics problem, and maybe it's similar to the tulips thing, and they're trying to figure out how to price tickets appropriately. Um, the the part of understanding the problem likely would come with someone saying, "Oh yeah, we have all of these spreadsheets and all of these things," and I think it would be very easy to get sucked into the problem in the ways that they currently do things, trying to understand enough to be able to map the problem. Do you have any advice for learning the space that you are operating in with the client well enough, yet kind of straddling that fine line of being able to quickly execute and provide ROI?
Well, we've developed an eye for use cases, but the mapping of the problem isn't a single layer. Um, um, if a prospect doesn't understand quantum, there may be a possibility they understand the issues with certain problems, either from a computer science standpoint or just an experience standpoint. But so our job is to listen to what they're saying and see if maybe the first step is we try to map it onto a computer science definition, because we know which ones of those we can easily get to the quantum. Um, um, but it's not I guess my answer is it's not a direct map. It's a multi-step process.
For sure. All right, thank you.
You're welcome. Anybody else have a question?
Ron, thanks very much for your very interesting presentation.
Just a general question. I thought your examples of business case studies were quite interesting when you're talking about optimization. I just wonder if you're acquainted of similar kind of application or case studies in engineering, particularly optimization of engineering designs or perhaps a more complex case in aviation or fluid dynamics. Are you acquainted with those applications?
Um, Not that I've seen, but again, on the gate-based side, there's been a big push. There's been a lot of work done in using gate-based quantum computers to solve uh, engineering problems that are highly involved with partial differentials, like um, particle flow systems or the Navier-Stokes algorithms for fluid dynamics and whatnot, or aerodynamics. Those are not, as far as I know, or I haven't seen, quantum annealers don't excel at that at the moment. But there are engineering plays that are going to uh, are definitely going to pick up speed again once the size and the depth of gate-based machines gets going. And it's not an area we've been involved with that much. But
That's fine. Yeah, thank you.
Mhm. Okay. Anyone else? Any questions on YouTube?
I see a good compliment. Thank you again, host and presenter and chat on YouTube. Yeah, George say
Well,
thank you, Ron, a great presentation. And Terry just made a comment. I'm realizing I've had a bit of decade-long bias against D-wave and quantum annealing due to early interest focusing on so much on the short algorithm. It's better for other things.
Yeah, I would comment on that. Annealing has really come into its own in the last couple of years. So 10 years ago, Terry, you weren't wrong. Okay. All right. Well, I would close out with saying, Helen, you are the best.
And you got a comment. Wonderful presentation. Thank you so much.
Thank you, everyone.
We also have our support from Debrada, who keeps a very low profile. But Debrada, thank you for all the stuff you've done also.
Absolutely, yes.
Ron, great presentation. This has been thought-provoking. It has changed my view on where this is at in a nicely positive way, and I appreciate that because, like I say, I've been inclined to be a little bit negative after being around this too long. So it's good.
Thank you for your
Terry,
comments.
Terry,
Thank you.
Thanks again, everyone.
Thank you so much. Take care.